Hi everybody, Physics Ninja here. Welcome to my big video on force problems review. This is what we're going to do today. We're going to look at problems dealing with forces. We're going to apply Newton's first, second, and third law in order to solve a multitude of problems. Not only are we going to do numerical solutions, we're also going to look at some conceptual questions. The problems deal with all kinds of situations, all right? We're going to look at forces of friction, static and kinetic. They're going to include pulleys. We're going to look at tension forces, for example. In total, I have 10 problems and 28 questions to look at. So this is what we do. So first thing you're going to do is you're going to download the PDF of the problems. That's in the description of the video. You can get the link there. The next thing you must try to do first is you have to try the problems out for yourself. Try to do them for yourself first, and then come back and watch the video. You're going to learn a lot more this way if you do this approach. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. All right, let's get started. All right, so here's the first problem. We have a block of mass 1.8 kilograms is being pulled up an incline at constant velocity by a string having a tension T. The angle of the inclined plane is theta, which is 34 degrees above the horizontal, as shown here in this figure. The coefficient of kinetic friction between the block and the surface of the inclined plane is given by this value, 0.25. All right, the first question we have is the magnitude of the normal force acting on the block. Well, what I would suggest with any problem dealing with forces is let's just draw the free body diagram. So we have mg acting down. What else? We have a tension. I'm just going to highlight that one, put it in green over here. That's the tension force. What else will we have? Well, there's a normal force, which is what the question is asking about. In this case, the normal force is perpendicular to the plane. And it's going up at constant velocity, which means there's going to be a kinetic friction because there is sliding going on right here. I'm also going to highlight this term. It's underlined here, but we're going to need that in just a minute. All right, so now let's go back to our question. It's asking about the normal force, right? And the normal force is being compared to the weight. Well, so let me just go ahead over here and just write the first part over here. So our weight we know is simply mg. Now, if you have a block on a slope, and you look at the only force here that's perpendicular to the slope is the normal. So the normal in this case, you should know this is mg, and you can write it as cosine of theta. So if I compare this to the weight up above, you should be able to convince yourself that the normal force in this case is going to be less than the weight, because you have the weight here in the front, mg, and then it gets multiplied by cosine of theta. So less than the weight of the block, A is the best choice for this first problem. The next one says, what is the tension in the string? All right, well, how would you calculate the tension in the string? For that, I am going to look at what's going on in the direction of the ramp. For a problem like this, I would probably suggest using a coordinate system where at least one of the axes is along the direction of the slope like this. So, all right, so we write down the sum of the forces here in the x direction. In this case, there are three forces. There's the tension, there's the friction acting down the ramp, and then there's also this component here of the weight that's acting down the ramp, which you can do, and then this sums to 0. So right away now I should be able to write an expression for my tension force. So the tension here equals to Fk, and then plus mg sine of theta. All right, now how do you write down Fk? Well, it's the coefficient of kinetic friction multiplied by the normal, mg cosine of theta, and then plus mg sine of theta. All right, at this point here, we should be able to write down what is our expression of the tension. You could substitute in all the numbers, 0.25 for that coefficient, 1.8, 9.8, cosine of 34 degrees, and then plus 1.8 again, 9.8, and sine of 34 degrees. All right, we put that in the calculator. You should get a tension that gives you approximately 13.5 newtons. All right, so that there corresponds to choice A. The string is now cut. Okay, so what does that mean? Well, it means there's no more tension, and the block slides down the inclined plane. What is the acceleration of the block in this case? So we have to be a little bit careful with this problem, because if the string is cut, what I would suggest is you redraw a free body diagram. Again, you're going to have your weight acting down. What else? We have our normal force, which is still there, which is perpendicular to the ramp. That does not change, but we no longer have this tension force. The other thing that changes is it says the block slides down the inclined plane. So that means we have to change our kinetic friction here. Fk should be pointing up now. So what I'm going to do now is, since they're asking me for acceleration, this sounds a lot like Newton's second law, right? Newton's second law has acceleration baked into it. So I'm going to choose a coordinate system here where this is x and that is y. And now let's add all the forces in that x direction. And in this case, they have to be equal to the mass of the block multiplied by the acceleration of the block. So what do we have here? What are the forces in the x direction? There's really two. So what I have to do now with the weight is you have to bring the weight down into, you have to break it down into two components. This is the weight in the x direction. This here is the weight perpendicular. I'll call it the y direction. For this problem here, you should know that the weight in the x direction is equal to mg sine theta. All right, so now let's go back to our Newton's second law and add these forces. So I've got mg sine theta that is acting down the slope, and I have kinetic friction acting up the slope, mu k times n. All right, now we could solve for acceleration. Here's acceleration here on the left-hand side. Let's take the right-hand side and clean this up a little bit more. And the way I do that is I substitute the value of the normal force. This is mg cosine of theta. And this is ma on this side. Now look what we have. We have the masses in all of the three terms, which means you could divide through by that mass. And now you're left with one expression for the acceleration. I'm going to factor out little g, and I'll write this out as sine theta minus mu k cosine of theta. All right, what we have to do now is simply substitute our values, so we get 9.8. Here you're going to get sine of 34 degrees minus 0.25, and then cosine of 34 degrees. Now just be careful, put that in the calculator, make sure you pay attention, and you should get 3.45. That is in meters per second squared. All right, let me box that up, and that looks like, well, again, to two significant figures, it would be 3.5 would be the closest answer. So A is the correct answer for that one. All right, the last one now, it says, well, suppose the mass of the block is increased, but the angle of the incline and the coefficient of friction stay the same. How is the acceleration of the block sliding down the plane change compared to the previous question? Is the acceleration going to stay the same, increase, or decrease? Well, this comes down to this step of the calculation right here. We notice that the mass of the block appeared in every single term. It's in the ma term, it's in this component of the weight, and it's also in the normal force, which means at the end, this guy right here does not depend on the mass. Therefore, it's going to stay the same in this case, so A is the best choice. All right, good problem to get started. Let's go to the next one. All right, here's problem 2. It says a box of mass little m sits on an inclined surface of a ramp and does not slide on the ramp. The ramp has a mass m and makes an angle theta with respect to the horizontal floor. The ramp box combination, they slide across the floor in the x direction with a constant velocity v. Which of the following is the correct free body diagram for the little box? Well, let's go ahead and draw that little box over here, and let's draw all the forces acting on that block. So first of all, we know there's a weight that's acting down. Now, what else? Well, it's in contact with the ramp surface, so there has to be some kind of normal force. That normal force to the ramp should be perpendicular to the ramp, so I draw something like this. So what else do we have? Well, we have to have something else, right? Because first of all, everything is moving at constant velocity, right? If things are moving at constant velocity, it means when I add the forces in any direction, I better get something equal to 0. So that's not only true for the x direction, it must also be true for the y direction. So you see right now, if I choose just this coordinate system, this is x and y, the normal component now would have an x component to it. So there has to be something else that opposes that. And that force there is going to be some form of friction. And since it's not moving with respect to the ramp, this here is going to be some static friction. I'll just call it FF for friction right now. So you have to have friction acting opposite of the ramp. Again, friction is always along the surface, okay? So this is what it looks like. So let's look at our choices over here. The one that looks kind of the best to me is probably free body diagram number 1. Now, free body diagram 2 and 3, they have those. So first of all, free body diagram 2 is missing the normal force. So you definitely need this normal force. So I would definitely rule that out. It also has this force over here, which is the force of the ramp. Well, this here really is the normal force. So free body diagram 3 has both of these contained. So you don't really need both of those. All right, the ramp can only push up on that little block. All right, so I'm going to choose A as being kind of the best choice. All right, question 9 says the total force exerted on the box by the ramp points vertically upward, is parallel to the surface of the box, points horizontally to the right. All right, so we want to know the total. So this guy is a little bit tricky right here. So what we have are 3 forces here acting on the block. The weight is what? This here is due to the earth pulling down on that block, right? So that one's definitely has nothing to do with the ramp. But this one here is what? It's going straight down, right? That's what we know about the force of gravity. It acts straight down. Which forces are due to the ramp? Well, I would say that the normal force is definitely due to the ramp. And, well, the friction also depends on the normal force. So this one here is also produced by the ramp. Now, if you're not clear now, how would you add both of those as vectors? Well, again, we have to use the fact that the sum of the forces have to be equal to 0 because the object is moving at constant velocity right here. And that's the key to this problem. So that means when you add up the blue vector, the force of friction, and the normal, they have to exactly cancel out the weight. So it must point vertically upward. So this is kind of a nice conceptual question right here. All right, question 10 down here says, suppose the magnitude of the frictional force acting on the block in the above scenario is FV. If the ramp and the box were moving at a bigger constant velocity. All right, so we're going to increase the speed here in that positive x direction. They're saying, well, what would happen to the magnitude of the frictional force needed to keep the box from sliding on the ramp? Do you think it would still be FV? Would we require a bigger force of friction, or we would require a smaller force of friction? Well, again, it comes back to this case right here. As long as the velocity is constant, okay, the sums of the forces must be equal to 0. Okay? It means that the normal force is still going to be equal, or sorry, the normal force is going to be like this. We're not changing the weight of the object, right? We're simply changing the speed. So it's not going to change the magnitude of any of those. The only way we would change the magnitude of the frictional force is if we were going to accelerate, right? But not at constant velocity. So in this case here, the best choice is also choice A. All right, let's move on to the problem 3 now. All right, problem 3 says we have a box of mass, little m, 15 kilograms, slides down a ramp with a constant acceleration here of 3.5 meters per second squared. The ramp makes an angle of 35 degrees with respect to the horizontal floor, and the ramp does not move. Question 11 says, what is the magnitude of the total force acting on the box? Again, we're looking at forces acting on the box. We have different choices here. We have MA cos theta, we have MA, and MA sine theta. Well, again, these are the forces acting on the box. We have mg like this. We have normal force, which is perpendicular to the ramp. And we may have some friction acting on that. So if it slides down, we may have some kinetic friction here, which I'll just call Fk. Now, if it's sliding down the ramp, I would probably choose a coordinate system that looks like this and like this. So what does it mean if it's sliding down the ramp or is accelerating down the ramp? It means if I add all the forces in that x direction here, which I'm showing going down the ramp, that must be equal to ma. So what are the forces acting in that x direction? Well, again, blocks on a slope, you typically break the weight down into 2 components. A component like this. This is the weight in the x direction. This here is the weight in the y direction, and we've done this before. The weight in the x direction is mg sine of the angle theta. The weight in that vertical direction is mg cosine of the angle theta. All right, what we want to know is the total force acting on the box. So that is kind of a trick here. Because you look at these choices, they all involve ma, right? But what does Newton's second law says? This says that the sums of the forces, this is really the total force acting on it. Right? The total force is actually ma. So that's it. You're all done with this one. So this one could be a little bit tricky. They might want it to put like ma sine theta because they might lure you into trying to select this choice right here. But this is mg sine of theta. The total force, you have to not only include that component, you must also include the force of friction. All right, question 12 says, what is the coefficient of kinetic friction between the box and the ramp? All right, so for this one now, we're actually going to apply Newton's second law right here. All right. So this is my equation. We're now going to substitute what are all the forces acting on this system. So I'm going to choose down to be positive. So we have this component of the weight here. So I have mg sine theta acting down. What else? I've got friction acting up. Friction I can write as a coefficient of kinetic friction multiplied by the normal force, which is mg cosine of theta. And this here must be equal to ma. That's the net force acting on it. Again, we see that the masses cancel out, so we've seen this before. And my goal now is to obtain what is this coefficient of kinetic friction. So you have to do some algebra in order to get it by itself. All right, so in order to get that coefficient by itself, I'm going to bring it on the other side. Okay, and I'm going to bring this acceleration term on this side. So it looks like we have g sine of theta. What else? Minus the acceleration of the block. And then I have to divide by, again, everything multiplying that coefficient of friction. So this is g cosine of theta. And now I substitute all my values. So I get 9.8. I get sine of 35 degrees minus the acceleration, which is 3.5. And here you get 9.8 and cosine of 35 degrees. All right, if you go ahead and do that in the calculator, I think I got an answer of 0.26 is the coefficient of friction. You go back to my choices, that probably looks like choice C would be the best answer for that one. All right, let's go to problem 4 now. All right, here's problem 4. A box of mass big M is 17 kilograms. It's free to slide on top of a frictionless horizontal table here. It's attached to a massless string and a pulley to a hanging weight over here that has a small mass of 12 kilograms. What we do is we pull on the top block over here in the direction away from the pulley. The weight is observed to move upward with a constant acceleration here. So that little guy's moving up at 1.9 meters per second squared. Question 13 says, how does the magnitude of the tension T compare to the magnitude of the applied force? All right, so we're really comparing both of the forces here acting on this top block. So what do we know? Well, this guy here is accelerating upward. If he's accelerating upward, it means that he's accelerating this way, right? Now, if an object of mass big M is accelerating to the right as shown, it means that there must be a net force acting in this direction. All right, and how do we get a net force? Well, there's two forces acting in that direction. Here's what the free body diagram looks like for that mass big M. There's a weight acting down. There's a normal force acting perpendicular to the table. What else? It's frictionless, so we don't have to worry about friction, but we know we apply a force F like this. And I also know that there is a tension. There's a string connected to it like this. And if we're accelerating to the right, the only way that this could happen is if the force F is bigger than the tension right here. So just making that argument, I think choice A is the best choice right here. Question 14, they say, well, what is the magnitude of that force? Well, in order to find the magnitude of F, we simply have to apply Newton's second law to this system. So this is what we're going to do right here is I'm going to write Newton's second law. So I'm going to add all the forces, and those have to be equal to ma, and I'm going to have to do it for both blocks because I don't know the tension right now. So let's start first with the big block M, and let's write down Newton's second law and then do it for the little block M. So for the big block, this is my coordinate system here. I'm going to choose a positive direction here to be in this direction, and positive y to be up. And again, I'm looking at only the forces in the x direction. So this would look like this: positive F minus the tension equals to the big mass times the acceleration of that big block. All right, how about the little block? Well, the little block is little m. It has a smaller weight, a little mg. And guess what? There's also a string connected to it. It's the same string as before. So that there is the tension force. So now we go back to Newton's second law, and this is how I would apply it. Now for this block, I'm going to choose the positive direction here to be the positive direction, the up direction to be positive. So this is what it looks like. We have T minus mg is equal to ma. It's the same acceleration, right? Both of those blocks have to accelerate at the same rate. All right. Now, what we have to do is, my goal is to find the force F. So there it is. So I need to eliminate the tension. The easiest way to eliminate the tension is simply to add up both of these equations. So if you do this equation 1 and equation 2 down over here, I'm just going to add up both of the equations, because in one of them I have minus t and I have plus t for the other term. So when I add them up, this is what I get. F minus mg equals to, again, it's m plus big M, and both of those terms multiply the acceleration. So here you go. Now I have an expression for that force F. I'll just bring this little mg on the other side, and this is what we get. M plus ma plus little mg. Now we substitute. Little m was 12 plus 17. The acceleration was 1.9. And then plus the weight of the small block. That's 12 multiplied by 9.8. All right, you go ahead and you substitute the numbers in the calculator, and I think I got 172.7 newtons. All right, let's go look at our choices now. Let's box this up. I think the best choice for this one is, well, 172.8, close enough for me. All right, awesome problem. Let's go to question 5 now. All right, here's question 5. We have a physics student is trying to pull a box of books of mass 40 kilograms across the floor as shown in the figure. The coefficient of static friction mu s is 0.49, and the coefficient of kinetic friction mu k is 0.35. The first question says, if the student pulls horizontally, so we set that angle theta equals to 0, what is the normal force? All right, so first thing you have to do is, if they're dealing with forces in a problem, what you should do is you simply draw the free body diagram. Now, here's what the free body diagram looks like. We've got our normal force. I have my tension now that's horizontal because I've set the angle equal to 0 degrees. We've got friction and we've got the weight. So you see from this figure right here that the normal force simply has to be equal to the weight. So that one there must be choice C is the best one. All right, so no need to do anything else for that one. Now the box is initially at rest, all right, and the student pulls at an angle now of 37 degrees. What is the minimum tension T required to start the box moving? All right, so first what I'm going to do is I'm going to get rid of this, and let's just make our tension now that's at this angle, because I'm pulling at an angle. I'll insert that angle over here, theta, which was 37 degrees. Now what you want to do here is you want to break the tension down into two components. You want this tension here, which is the x component. This is going to be T cosine of the angle theta. And I also have a vertical component of the tension, which is T sine of the angle theta. Now what you can do is you could just set up an equilibrium condition right here. And then if that force gets a little bit bigger than whatever the equilibrium condition is, then you know it's going to start to move. All right, so let's just set up that equilibrium condition. And in that case, what we're going to do here is we're going to use the maximum force of static friction. So this is what it would be. As long as T cosine of theta, this component of the tension here, imagine here it equals to this maximum force of static friction. Right? If those forces are equal to each other, it's simply going to be at rest. If this tension T cos theta is a little bit bigger than this, then it's going to start to accelerate. So that'll be how we're going to find our minimum force of tension required to get it to move. Now the force of static friction, the maximum value is simply mu s multiplied by the normal. and that is mu s mg. Oh, one important problem right here. Actually, I'm going to come back to this. I nearly made a mistake myself. See what happens. So what is the normal force in this condition right here? In the first part here, we said the normal was equal to the weight. However, look what happens in this case. We also have this component here of the tension that is helping to lift the block. So I would call this equation 1. We're going to come back to it. If you look at the forces here in that vertical direction, this is what it looks like. You should have the normal plus t sine of the angle theta minus the weight. This here equals to 0. There is no force in that vertical component right here. So what do we get for the normal force for this problem? So now I just isolate it. So I bring mg to the other side, and I bring this component here of the tension. I also bring this onto the other side. So this is a really important part of this. All right, now I'm in a position where I could substitute the normal force back into my equation right here. So the normal force is mg minus t sine of the angle theta. And t cosine of the angle theta is on the left-hand side of this equation. So my goal now is simply to solve for t. So what you have to do here is you bring this whole term here. Again, don't forget it multiplies the mu s. You have to bring that on the other side and then isolate. So that's what I'm going to do. So I'm going to call this t. This is going to be cosine of the angle theta. Now it's negative on the right-hand side. When you bring it on the other side, it becomes positive. And this is going to be mu s cosine of the angle theta. And that here equals to mu s multiplied by mg. All right, so now I have my final expression for that tension force. Again, this is to remain in equilibrium. If the force is just a little bit bigger than this, it's going to, now look what I've done over here. I have done just a horrible job at this problem, but we're just going to keep on going. This was sine theta, so I have to bring this on the other side, and sine theta over here. All right, I think I'm in a position now where I could substitute my numbers. 0.49. What else? The mass was 40 kilograms. Little g, we're going to take 9.8. And now we have all these angular terms here. So we have cosine of 37. We have the coefficient of static friction, which was 0.49. And then I have sine of the angle of 37 degrees. All right, assuming I didn't make a mistake, I get a tension which is approximately 175.6 newtons. And that there looks a lot like choice A to me. Phew. All right, let me box that up. All right, great job. Now let's look at the third question here. It says if a student applies the minimum force required to get the box moving for 5 seconds, all right, which of the following best describes the motion of the box? All right, well, think about once it starts to move, right? Once it starts to move, what happens? As soon as it starts to slide, right? Once it starts to slide, what happens to the friction? We're no longer using static friction right here. We have to go to kinetic friction, okay? Now, let's think about kinetic friction versus static friction. This here's the coefficient of static friction, and this here's the coefficient of kinetic friction. So this force right here, this force of kinetic friction, is actually less than that force of static friction, the maximum value. Which means that all of this means that you're going to have a net force that is pointing to the right, because we still have our tension, and now we have this smaller force of friction that's acting to the left. So what does it mean? It means that the box is going to have a net force in this direction, which means it's going to accelerate in that direction. So it's not going to move at constant speed because it has to have an acceleration. It can't be choice A. The velocity of the box will continue to increase over the 5 seconds. Yes. And this choice C just doesn't make any sense. It's going to start to move and slow down. That's way too complicated for me. Choice B is the best answer for this problem. This is a kind of a tough problem. All right, here's problem 6. We have an inclined plane with an angle theta. It has a rough top surface with a coefficient of static friction mu s. and kinetic friction mu k. Mass m, little m, sits at rest with respect to the plane, and it's attached by an ideal string over a massless pulley to a hanging mass. All right, question 10 says, which of the following is the correct expression for the maximum value of the hanging mass, such that the little mass m does not move, it remains at rest? So what we want is an equilibrium condition here when we start adding more mass over here. Right? When we add more mass, again, eventually it's going to start to fall. But what is the maximum mass that you can have on this system before it starts to fall? All right, so first thing we do is we're talking about forces, we're talking about mass and so forth. I would suggest you draw a free body diagram. So let's look at that hanging mass. The hanging mass is straightforward. It simply has a weight, mg, and it's connected by this string, so you have a tension force. Now the other block, little m, is on the slope. So its free body diagram looks something like this. It has a weight, little mg, acting down. There's a normal force perpendicular to the ramp. Again, it's connected by the same string, so it has that tension force. And now look at the way I've placed static friction. Static friction is trying to stop it from sliding up as I add more mass. All right, so the goal now is just to write down Newton's laws for this problem in equilibrium. So we're going to start with the big mass. This one's pretty straightforward. If you choose down to be positive, again, it doesn't matter. Nothing is accelerating, so you have mg minus t equals to 0. All right, so the weight and the tension have to balance out. For the small block, m, again, we're simply going to choose a direction. I'll choose up here, up the ramp, to be the positive direction. So this is what it looks like. Again, you have to break the weight down into two components. The component parallel to the ramp for the weight is the weight in the x direction. I'm going to call this the weight in the y direction. Okay, so we're in a position now to write down the forces along the ramp direction. This is what it looks like. I have it as T. I have a component of the weight that's acting down the ramp, so that is mg sine of the angle theta. And then what else? Now I'm also going to have a force of static friction. And the biggest that you can make the force of static friction is the Fs max value. And again, I don't want anything to move, so you set that acceleration equals to 0. All right, so next thing you could do is we could substitute what is this maximum force of static friction right here. This means it's the coefficient of static friction multiplied by the normal force. And the normal force for this problem is mg cosine of theta. You get that from looking at the forces in that perpendicular direction to the ramp surface. All right, the goal was to find what is this maximum mass that you can have. Notice that all of these choices here involve the coefficient of static friction and the angle and the little mass. They don't include the tension. So one way we're going to do this is to eliminate the tension. To eliminate the tension, what you can do is you can add both equations up. So you get mg over here, and then we simply will eliminate the tensions, and I'm going to bring both of these other terms here on the other side. So I'm going to get mg sine of theta plus the coefficient of friction, little mg cosine of theta. Okay, now we're not quite there, but all we have to do is just look at the choices here that we have. I can divide through by little g. Little g appears in all of the terms, so you can get rid of it here, here, and here. So, and if you wanted to, you could factor out the little mass m, but just comparing them, you should see that one of these choices actually appears. Look at both of these here. Just got to be careful that you select the right one. It's really choice D is the best one because you're adding this extra contribution due to friction over here. Okay. So D is the correct choice for that, and you can see that from this solution right here. All right, question 11 says, the string is suddenly cut, and the mass m begins to slide down the plane with an acceleration a. What is the correct expression for that coefficient of kinetic friction? So if the string is cut, we have to modify our free body diagram. All right, so what I'm going to do is I'm just going to draw a new free body diagram because it's a completely different situation here. We still have mg acting down. I still have my normal force perpendicular to the ramp. And now it slides down. So guess what we're going to have? We're going to have friction that is acting like this, right? This is the force of kinetic friction now because it's sliding. All right, so when you have an object sliding down a ramp, I would choose this type of coordinate system here. And we're going to apply Newton's second law in order to find this, right? So you add up all the forces, for example, in this x direction. That has to be equal to mass times acceleration of this block. You notice that a lot of these solutions here include the acceleration of that block here. All right, so what are all the forces acting in this x direction? Again, we have that component of the tension, which is the component of the weight, which is this guy. That's still going to be there. That's mg sine of the angle theta. And what else? Now we also have kinetic friction, but kinetic friction is acting opposite of that. So you get minus mu k multiplied by the normal, which is mg cosine of theta. So we can have to simplify this expression. You could eliminate the masses. They appear in all of the terms. And now look, I'm asked to solve for what is this coefficient of kinetic friction. So we have to do a little bit of algebra in order to get this. But you're going to get mu k. It's negative on this side, so I'm going to bring it to the other side of the equation to turn it into a positive value. And then I have to be careful with the algebra here. So I get g sine of theta minus the acceleration, and then I have to divide by everything here by a g cosine of theta. All right, I think I have my expression kind of in a pretty simplified form. So what we're going to do now is let's go back and make sure we select the right choice. First of all, this one here wouldn't make any sense because it has the mass here, and we should know that the coefficient doesn't have any units, so it shouldn't have any mass over here. It looks to me like probably the best choice here. It looks like choice A is the exact choice that I have. Yes. Okay, so I'm going to go with choice A. That's probably the best choice. A nice kind of application. Again, more complicated because you've got this angle and the wedge here, but applying Newton's laws, do a free body diagram, select a coordinate system, and you're well on your way. All right, here's problem 7. We have a 7 kg block, starts from rest, slides down a frictionless ramp that makes an angle of 26 degrees with respect to the horizontal floor below. At the bottom of the ramp, having slid a distance d1, the speed of the block is observed to be 18. So that's kind of right over here. This is 18 meters per second. All right, question 12 says, what is the distance d1 that the block slid along the ramp? All right, well, we do know that the initial velocity is 0. It started from rest. And we know that the final, at least on the ramp, is 18 meters per second. What we need to know is what is the acceleration of the ramp, right? What is the acceleration of the block when it's sliding down over here? Well, imagine the forces. You have the weight acting down. We've got our same normal force, which is like this. And for a block on a slope, you're best to use a coordinate system where you have a positive axis acting in the direction of the acceleration. There's only one force that is accelerating this block down the slope. It's this component of the weight. We call that the weight in the x direction. So the weight in the x direction is mg sine of the angle theta. You have to know that for a block on a slope. That is the only force acting in that direction. That must be equal to the mass times the acceleration. So we know that the acceleration of the block is given by this value right here. So all we're going to do now is do some kinematics. So one of the kinematic equations looks like this. It's v final squared equals to v initial squared plus 2 times the acceleration multiplied by the displacement. In this case, it's the displacement d1. Now my initial velocity is 0, so you cancel that out. And my goal was to find d1. d1 is v final at the bottom of the ramp divided by 2 times a. So now we substitute, right? Well, we're going to have v final squared, and my acceleration is g sine of theta. So we put in our numbers now. We get 18 squared to 9.8, and this will be sine of 26 degrees. All right, so I get a value of d1 that should give me something like 37.7 meters. All right, that looks like choice D to me is the best choice. All right, question 13 says, after reaching the bottom of the ramp, the block slides onto a horizontal floor with an initial speed of 18. the coefficient of kinetic friction between the block and the floor is 0.4. From the moment it reaches the floor, how much time does it take to stop the block? Again, this is almost like another kind of kinematic style problem. So, I mean, this is what it looks like once it's sliding. You have mg acting down. We've got, again, the normal force acting up. And the block is moving to the right, but it's sliding, which means you have to have some kinetic friction here in this section that's acting to the left. So that force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal. And the normal force in this case is simply equal to the weight. So how would we find the time though, right? It starts off right here with an initial speed equal to 18 meters per second. But at the end of the day, it ends up being right over here, and it has a velocity equals to 0 meters per second once it stops. So if we think about one of the kinematic equations that involves time, we would have this one, v final equals to v initial plus the acceleration of the block multiplied by time. And in this case, it's v final here, which is equal to 0. So how would we solve for the time? Well, you'd bring v0 on the other side, and then you'd divide by the acceleration, so you'd get minus v0 divided by a. Now it looks like, well, v0 is 18. Well, what about the acceleration? So again, I need to find the acceleration when I'm on this flat section. In order to find acceleration, you use the second law. So what do? Well, we add up all the forces in that x direction. Again, there's only one force, and that force is acting opposite of the motion. So I'm going to call that the negative direction. So this is what Newton's second law looks like for that block on that flat surface. There's only one force, the force of friction. It's acting to the left. That's it. So my acceleration of the block here ends up being a negative number. That's just associated with the direction. And now you end up substituting that value back into my time equation here, and you get minus mu k multiplied by little g. So this is what you get. Those negative signs cancel out, and now we can substitute in all our numbers. So we get 18 for that initial velocity here, right, when you're just in that flat section. The coefficient of kinetic friction here was 0.4, and then multiplied by little g, 9.8. All right, I get a time. You put that in the calculator. I think I get something of around 4.6 seconds. So let me box that up, and that looks like choice B is the correct answer. All right, not too bad. Question 14 says, if the mass of the block in the above problem were doubled, the time required to come to a complete stop. So what would happen to the time here? Well, let's think about our time equation. It depends on this initial velocity here, v0, and it depends on the acceleration. Does the acceleration of the block here, when it's sliding, depend on the mass? Over here, it does not depend on the mass because the mass cancels out everywhere. So definitely this term wouldn't change. What about this 18 meters per second over here? We also see that the acceleration of the block when it's on the ramp also doesn't depend on the mass. So at the end, if you change the mass, you're not going to change anything with this problem. Everything is basically just going to stay the same. So this is one of the advantages of working with algebraic equations and not substituting the numbers right away. You can see right away there is no dependence on the mass for any of these accelerations here, whether it's on the ramp surface or whether it's on the flat surface. All right, that's it for this one. Let's go to problem 8. All right, here's problem 8. We have a box of mass of 0.4 kilograms is moving along a stationary ramp. It's moving up the ramp like this shown in the figure. The box's initial speed is 1.4 meters per second, and the angle between the ramp and that horizontal plane is 24 degrees. The coefficient of friction between the box and the ramp is 0.32. All right, question 12 says, what is the magnitude of the box's acceleration as it's moving up the ramp? All right, so how do you find the acceleration of the box? Well, guess what? We are going to apply Newton's second law. That has the acceleration in it. Going to draw a free body diagram on that box. We're getting good at free body diagrams now. What else? We've got the normal force acting perpendicular to the ramp. And as it's moving up, we should have our kinetic friction force here, Fk, acting down the ramp. All right, next thing we want to do is we want to apply Newton's second law. So again, for this one here, I'm going to use the coordinate system that's been provided in the problem over here. So I choose positive up the ramp and negative to be down the ramp. So how would I sum up Newton's second law? You add up all the forces, they have to be equal to the mass times the acceleration. Again, if I'm looking at this x direction, there are two forces acting down. There's a component of the weight, which is minus mg sine of the angle theta, and then minus the force of kinetic friction. All right, now we have to do a little bit more work. Again, minus mg sine of theta. Let's substitute in our force of friction. It's mu k multiplied by the normal. The normal for the block on a slope is mg cosine of theta, and that equals to ma. Just as we did before, you can cancel out these masses, and now we're left with our expression for the acceleration. I'll factor out a minus little g, and I'm left with sine of theta. Be careful over here, plus mu k cosine of theta. So now we could substitute in all our numbers. Minus 9.8, sine of 24 degrees, plus 0.32, cosine of 24 degrees. Put that in the calculator. At the end of the day, I think I get something like minus 6.85 meters per second squared. Now the question asks for just the magnitude of it. The best choice over here is choice A. That is the acceleration as it's going up the ramp. Let's look at question 13 now. It says, what is the direction of the box's acceleration as it moves up the ramp? Well, the acceleration is going to be down because look at these forces over here. Both of those forces are pointing down the ramp. And you can also see by this sign over here. So that there should be in the negative x direction here because in this coordinate system we're taking the positive direction to be up the ramp. So to be consistent with this problem, B is the best choice. All right, question 14 says, eventually the box is observed to slide back down the ramp with another acceleration. This time we're going to call it A down. Compare the magnitudes of these two accelerations when it's going up versus when it's going down. So as it's going back down the ramp, what I'm going to do is I'm going to draw another quick free body diagram. I still have mg acting down. I still have my normal force, which is perpendicular to the ramp. But look what happens now. If it's sliding down the ramp, you better have your kinetic friction acting up the ramp. So what does this mean? It means we have a component of the weight that's acting down, and we have the kinetic friction that's acting up. So there's going to be a net force here acting down the ramp. However, it's not going to be as big as in this first case. Because look what we have over here in this first case. We have both of these terms that are in the same direction. When they are in the same direction, they come up and have the same sign over here. When we're going to break this weight down into components, we have the weight here in that positive x direction or negative x direction for this coordinate system. But you see that these two forces, the weight in the x direction and the force of kinetic friction, are opposite of each other. So that means you're going to get an acceleration that is going to be smaller when it's going down versus when it's going up. Okay, because of that. So a little bit of a trickier problem, but you have to argue it by looking at the forces and which directions the forces are acting. All right, let's go to problem 9 now. All right, here's problem 9. We have a solid cube box of mass of 4 kilograms is being pushed along the floor by a horizontal force F, which is 12 newtons. The box is observed to move with a constant velocity of 0.3 meters per second. Let me highlight that term. Here's question 10. It says, what is the coefficient of kinetic friction between the box and the floor? Again, always best to start with a free body diagram. So we have the mass mg acting down. We have our normal force acting up. And we're going to have some kinetic friction because we're sliding. So we have Fk, which is pointing to the left, opposite of my applied force. Since it's moving at constant velocity, I better have that the sums of the forces have to be equal to 0. That's Newton's first law at work right here. All right, so we want to get to a coefficient of friction. So guess what? The coefficient of friction is inside this definition of the force of friction. So let me go ahead and just work on this equation a little bit. Bring Fk on the other side. And now I substitute what my value of the force is. The magnitude of the force of friction is written as a coefficient multiplied by a normal. That's a coefficient, and in this case, the normal force here is simply equal to mg. So that must be equal to this applied force. So here I get a value of the coefficient of friction, which is this applied force, divided by mg. All right, you substitute my numbers now. So I get 12 newtons for this. I get a mass, which is 4 kilograms, and my little g is 9.8. All right, put that in the calculator. I should get a coefficient of friction that's approximately 0.31. The best choice for this problem here would be choice C. All right, not too bad. All right, let's look at the next question, 11. A second box is made of the same material as the first, but it's half the size as the first in every dimension. Okay, it's subjected to the same force. So we still have this 12 Newton force over here. Well, what happens with the rest of the forces? If it's exactly half the size but made of the same material, it means that its mass or its weight is going to be half. This would be the weight here acting down. That also means that this normal force here, I'll call it N2 in this case, is also going to be smaller. So what do you think happens to the friction force? The friction force in this case here, Fk, is going to be half of whatever value we had at the top, because the friction force depends on the mass over here, because it depends on the normal force. So let's read it. Let's see what all the choices are here. Do we think it's going to move with the same constant velocity as the first box? Is it going to move with a constant acceleration? Or does it move with a constant velocity 8 times that of the first box? So whether it's constant velocity or it's accelerating, you have to look at these forces. And what we're going to have here is, since this force here is still equal to 12 newtons, and now this force here got smaller than the previous case, we know that the 12 newtons is going to be bigger than whatever the force of friction is. So that means that the box here has to accelerate, all right? There is no other way around it, okay? Because my applied force is bigger than the force of friction in this case. All right, not a bad problem. Let's go to our last problem, problem 10. All right, here's the last problem, problem 10. We have a box of mass M1 of 10 kilograms is placed on a frictionless surface. A smaller box of mass M2, 3 kilograms, is placed on top of that large box. The box is initially at rest. A horizontal force, F, is applied to the lower box, pulling it to the left as shown in the figure. The coefficients of static and kinetic friction between the two boxes are 0.25 and 0.29. Question 7 says, initially the two boxes are observed to move together. It says the small box remains on top of the large box. What is the direction of the friction force applied by the small box M2 on the large box M1? And we're given some different directions here. So what I would suggest here is you always start with free body diagram if you're going to look at forces. So if you look at that top one, well, we have a weight, M2G. What else? We have to have a normal force. The normal force, I'm going to call it N2, acting like this. What else? Well, we say that both boxes are observed to move together. So there has to be some other force here acting in this X direction for this block M2 to be moving to the left. And in that case, the only other force that could be acting over here is this force of static friction. All right, let's look at the bottom block now. The bottom block here is M1. It has a weight, M1G. There is a normal force from the bottom surface pushing up on that block. I'm going to call it N1. Now there is going to be another force because the block M2 is pushing down on M1. So I'm going to call this one here N2. This is an action-reaction pair with this top force over here. What else? Well, I have my applied force F. That one is pulling on that, so you definitely have this force. All right, now the question is, what do you do with this force of static friction? This force of static friction is really object 1 acting on object 2. Right? Because we're looking at forces here on mass M2. So there must be an equal and opposite force of 2 acting on 1. And that means it has to be in this opposite direction. The same force of static friction here, this would be 2 acting on object 1. And that is exactly what they're asking for. What is the direction of this friction force applied by the smaller block, 2 acting on 1? So we have to have it acting to the right. So B is the correct choice just by looking at the free body diagram like this. All right, what else we have? Question 8 says, what is the maximum force that can be applied before the small box begins to slide relative to the large box? All right, well, for this one, we are looking at what is this maximum force of static friction. The maximum value of static friction here between both of those boxes is mu s multiplied by the normal. And the normal force in this case is going to be what? Well, we're looking at the normal force N2. So N2 is written like this. So right away I can write mu s, that coefficient, multiplied by m2g. All right, so this is the only force here acting on that block M2. So guess what? If you write down Newton's second law for that block, I get M2A must be equal to this maximum force of static friction. All right, so this is an equation that I have here for the dynamics of that top block. Let's also write down now and connect it to what's going on here with the second block. So for the second block, what I have is if I write down Newton's second law, well, the mass is m1. Its acceleration is also going to be a if they slide together. So this is also an important point. Now, how do we add the forces here? Well, we're going to add all the forces here in this horizontal direction. I have the force F, which is acting to the left. I'll take that to be the positive direction. And then I have minus this force of static friction here. Well, the force of static friction is what I just determined over here. It's mu s m2g. So my goal is to find what the force F is, so I simply have to write it in terms of quantities that I know. What you can do is, for example, let's just do a little bit of math here. If I add up both of these equations, what I'm going to get is I'm going to get this force F, which is equal to, again, all of these friction terms are going to cancel, because in the top equation I have plus mu s m2g, in the bottom one I have minus the same term. So when you add up the equations, those terms disappear, and what you're left with is something like this. Now it's still written the force F in terms of the acceleration, but you see from this equation here that those masses m2 cancel out, and the acceleration is simply equal to mu s times g. So what you can do is the last step over here is simply get rid of the acceleration and write it as the coefficient of static friction multiplied by little g. So all we have to do now is simply substitute our values. So the mass m1 was 10, mass m2 was 3, the coefficient of static friction was 0.29, and then little g is 9.8. All right, we put all that in the calculator, and I think I got something like 36.9 newtons. All right, you go look at our choices, and clearly the best choice over here is choice A for that maximum force of, that maximum applied force that we can have so that both of these blocks here have the exact same acceleration and they don't slip one relative to the other. All right, folks, that's it for this problem set. Hopefully you enjoyed these, and we're getting you ready for your exams this semester. We'll see you next time.